Alright, Physics 11. This is the first video of our fourth unit, which is about waves and mechanical waves. We're going to talk about the overview of mechanical waves action, like what exactly constitutes a wave, why do these things move. We'll talk about different types of waves, the features of a wave that are common to all of those types of waves. We'll do some example problems about frequency and period and wave speed, and then we'll talk about interference and beat frequency. Briefly. This is something that we did in class, but I'll talk about it. So we're just going to start. Here's a wave. It's a cool, this is the sky above a city. I just found this cool GIF about it. Here's what we're talking about today, some different terms about waves. We're going to investigate the relationship between wave frequency and speed. We're going to distinguish between longitudinal and transverse waves. And then over here, we're going to illustrate the principles of wave superposition. So let's start with, what is a wave? So first things first is a wave. A lot of the waves that we talk about, like water waves, sound waves, springs, waves and springs, waves and ropes, shock waves from a bomb, all of those are called mechanical waves, and that's what we're talking about here, mechanical waves. Light is not a mechanical wave, it's an electromagnetic wave. We covered that in grade 12. I did a brief explanation of that in the thermal energy concepts video. And we've also observed gravity waves recently. They're also not mechanical waves. Those are a different kind of wave entirely. What a wave actually is, what a mechanical wave is the transmission of energy through a medium. That is the physics definition of a waveform. But it's not enough to say that the energy gets transmitted. A wave requires an actual repeat. You can't define a wave unless it's repeating. So here's kind of a diagram of it. For example, here, there's a slinky attached to the wall. You compress the slinky, you're giving it potential energy. That potential energy causes the slinky to expand, but that compresses the next part. That compresses the next part, that compresses the next part, and the pulse moves through. Or if you do a pulse like this, you can move it away from the center. That gives it potential energy. As it tries to move back, it needs to push off of the next thing. The next thing gets pushed up, and the next thing gets pushed up, and the next thing gets pushed up. This is probably easier to see on this PHET simulation. You can see the link to that down in the description. I've got it here with very low tension and no damping. And you'll see that when I move this particle, the other particles want to follow, but there's a time delay because it takes time for the force to affect the next particle. So you'll see that it takes time for the force to affect the next particle. This part of the wave doesn't know that it's been touched yet. Now it does. And if I move it back, right over here, it sees like nothing's wrong until it gets touched. So that's kind of the general idea. You have potential energy, and then the force is transferring the potential to kinetic, and then back, and back. And so we can make this oscillate like that, and I can reduce the frequency to something a bit more manageable. Let's take it to 0.5. And I can move it up and down. You get the same idea. It's just a constant transfer. This thing starts, hang on, we'll stop it here. This is up high right now. And so these want to follow because it's in a, the force is pulling them upwards. But as the force pulls them upwards, they end up going down afterwards because of basically Newton's third law. If they want to pull something up, they themselves have to get pulled down. So this thing just pulled a bunch of stuff up. It is going to get pulled down as a consequence. Pulled down as a consequence. And off it goes. Now, a real wave in the real world, there's always loss because it's a conversion of energy, and any conversion of energy carries some heat loss. And that's what we call damping, right? That's that second law of thermodynamics. So if I put some damping on here, right, notice that if I make some of the energy get lost as heat, the wave doesn't propagate nearly as far. And this is what really happens, right? Waves don't perfectly propagate forever. Yeah. So, I can reduce the damping and you'll see it kind of get a little bit better. So it's a trade-off of energy, back and forth. And it can be energy like this, or it can be linear, or it can have different kind of things. I can also just make a pulse, send a pulse, and notice that the damping is slowing it down. Right? Send a pulse, and the damping is going to slow it down. So that's the basic idea of energy. It's energy of waves. It's energy moving through a medium, and it's the force of the medium that is actually converting potential energy into kinetic, back and forth. So depending on the medium, you get different waveforms. It all starts with a displacement of the particles away from some kind of equilibrium. So if this is equilibrium, I'm going to displace the particle, boop, and I displace it away from equilibrium. And that displacement from equilibrium travels down the wave. But notice the particles aren't moving, right? This particle stays in the same place. It just, the displacement of the particle moves. So that's kind of important to talk about. Yeah. And they propagate, and this is down to Newton's third law. So if I move this back over to the right, this is down to Newton's third law. When you go back to the equilibrium, you have to push off of your neighbors. So this thing is far away. It wants to come back down. When it wants to pull itself down, it pushes up on its neighbor. That one wants to come down, it pushes up on its neighbor, and so on and so forth. Very much just a Newton's third law thing. This leads us to the importance of the medium. Because it's Newton's third law and it's transmitted through a force, that means that that the wave speed will change depending on the medium that it's traveling through. So denser mediums usually transmit waves faster, and materials with more tension transmit waves faster. So we can see that in our little demo here. I can actually change the tension. So here's the normal pulse. Off it goes. If I change the tension to high, to a medium tension here, if I change it to a medium tension, that means that the particles have more force trying to push them back to equilibrium, which means that they will affect their neighbors faster because there's more acceleration, right? More force means more acceleration with the same mass. So it takes them less time to get back to equilibrium. Because it takes them less time to get to equilibrium, it takes their neighbors less time to get pushed back up. And so you'll see this wave travel faster. See it travel faster. If I go to the high speed, it travels even faster than that. Travels even faster than that. We can see at the low amplitude, right? This goes away pretty quickly. The high amplitude at the high tension, it goes faster. We can also change the amplitude here. I can make it a bigger pulse or a smaller pulse, but it doesn't change the speed. Yeah, so that's the medium. This is how basically musical instruments work. Here I've got a balloon, and here's a normal balloon. It has an equilibrium point. If I stretch it away from the equilibrium point, it comes back. Right? But if I do it on one side, it'll actually transmit through, because now we've got a wave coming through. And you can hear the frequency, right? If I stretch it, now there's more force that's going to try to pull this stuff back. And you get a different frequency, and that means that there's a different speed happening in the sorry, it's not exactly a different speed, but it's related to the speed because it's just going back and forth faster. Yeah, more tension means you have a difference in the wave speed. This is a faster wave than this because there's more force for the same amount of mass. So denser is usually faster, springier is usually faster. So springier is really kind of the operant word here. It's kind of related to the density of the material, like how many particles are next to each other, but not necessarily. So, for example here, steel has a speed of sound, or a wave speed of about 6,000 meters a second. Aluminum has a wave speed of 6,420, which is faster than steel, but aluminum is a lot less dense than steel. Stuff like that. Or, for example, helium is less dense than air, but helium has a faster speed of sound than air. And here's the speed of sound in different media in the body. Fat and muscle have different speeds of sound, and bone has a fast speed of sound. This is how ultrasounds work. They use this difference in speed to make a difference in pictures. And they've actually got the densities here. You can see that aluminum is maybe 3 times less dense than steel, and it's got a faster speed of sound, which is pretty interesting. And beryllium has a very, very, very fast speed of sound. It's got a very fast return of energy, and it's even a lower density than aluminum. Beryllium is actually what they make a lot of springs out of, because they want something that can return energy quickly. So a lot of springs are made out of beryllium because of this springiness of it. That's that. We're going to move into types of waves. So I'm going to pause and get into types of waves. And we're back. We're into different types of waves. So a single pulse is not a wave. If you look at the applet, right, I can make a pulse and go pew, or I can make it oscillate. Take away the damping. Right, so this is a wave. This is wave motion, but that pulse is not considered a full wave. A wave is up and down, up and down, up and down. So that's the type of wave. Waves are the repeating pattern of displacement. So here's a wave, there's a wave, there's a wave, there's a wave, there's a wave. They don't necessarily have to be sinusoidal. That's that nice shape, the tuning fork shape. They can be different different shapes. And then a little thing, like here's a cool shockwave GIF. You can see the shockwave propagate through the clouds. It's a pressure wave, and so the pressure from the explosion of this mountain, which is a volcano, that sudden change in pressure is what's causing the clouds to form. And you can really see it. It's really cool. It's just a sudden vapor cloud from the change in pressure. A technical term for going back and forth around a set point is oscillation, and each repeat is called one cycle, coming from the fact that it can be created by, I'll move this back over, it can be created by something moving in a circle. So you can imagine this is just pushing a rod up and down. So a cycle is one circle, one cycle of this. One cycle. Different waves have different timbre. So they have timbre. Timbre is the shape of the wave. So both of these waves have the same frequency. So you'll kind of hear the same tone, but they have different timbres. So you're actually going to hear a different kind of sound. It's hard to explain, so I'm going to pause and I'm going to find a wave generator. And I'll show you much better using the wave generator. Just a sec. Okay, so I found this tone generator online, and I'm going to mute my microphone every so often so you guys can hear the pure tone coming off of here. Obviously, link in the description for this thing. So I'm going to generate a 220 hertz tone, and you can listen to that 220 hertz sine wave tone. Notice that this is a sine wave, So that's this shape here, 220 hertz sine wave tone. So I'm going to mute. So that's a sine wave tone at 220 hertz. Next, we're going to still keep the 220 hertz, but we're going to go to a square wave. And so it's still going to be the same like pitch, but it's going to be a different timbre. So you'll hear a different thing. So remember that one was kind of like a really nice steady hum. This one's going to sound different, so I'm going to mute. That was probably a lot more unpleasant. Square waves sound interesting. So that's a square wave. We're going to go triangle wave now. I'm going to mute. That one probably sounded like something between the two, between the sine wave and the square wave, because it's kind of got features of both. Then the last one here is the sawtooth, where it's going to very suddenly jump, just like the square, but only on one side of it, and it's going to ramp up on the other side. So let's try. Yeah, so that one's kind of not very pleasant. We don't like those sudden drops in pressure, the sudden changes in air pressure. I'm going to go through each one in turn with my mic muted so you can hear the difference in what we call timbre very effectively. So here we go. I'm going to go back to here, and I'm going to mute, and we're just going to go through each one one by one. Let's go back to sine wave, and we'll just move right through it. So you could kind of hear that sine wave kind of underlying the entire time, because your brain likes to interpret things as sine waves. So you can kind of hear this basic sine wave under each of those complex tones. And this is what causes timbre. This is what makes a flute sound different from a violin. Makes different human voices sound different, even though they're both singing the same note. It's from resonance that happens in our throats. And in musical instruments, resonance that happens within the musical instrument. This is how, a guitar and a violin can play the same note on their string, but you know that one is a guitar and the other one is a violin, just from the shape of the resonating cavity. It's pretty interesting. Next, we're going to get into different types of waves. There are three major types of waves. The first one is the classic transverse wave. This applet is showing a transverse wave. If I slow down the tension, you'll see a nice, medium speed. Here we go. You'll see a nice transverse wave there. There's a transverse wave. The particles are being moved side to side across from where the equilibrium line is. Across from the equilibrium line is. So like if I go manual, I can move it side to side away from equilibrium, and they want to come back to equilibrium. That is a transverse wave. Transfer across. Right, transfer across. It's perpendicular to the direction of travel. Let me move my thing over here. Transverse wave. Guitar string waves are a good example of this. When you pluck a guitar, you're plucking it away from the equilibrium line, and so it'll vibrate in a transverse direction. Longitudinal, as pressure waves, the deflection is in line with the direction of travel, and it creates this pattern of what's called compressions and rarefactions. Notice that the particles are moving back and forth in the same way that the wave is traveling here. Back and forth, back and forth, back and forth. It creates compressions and rarefactions. Compressions where the particles are close together and they want to get far apart, and rarefactions where the particles are far apart and they want to get close together. Just like here we have crests and troughs, where the crest is the top of the wave and the trough is the bottom. Both of them are away from equilibrium. Same here. The compression and the rarefaction are both away from equilibrium. The equilibrium sits right between the compression and the rarefaction. And that's what sound waves are when we, for example, clap, right? When we clap, we are compressing air, and the compressed air wants to get out, and that hits other air particles, which hit other air particles, which hit other air particles, and they leave lower density behind, and that lower density wants to get filled in, so you get this propagation of air, propagation of sound waves. But the air molecules are just kind of boop, coming back, but they're hitting other molecules and hitting other molecules, and that's where you get the sound of a clap, the sound of anything, really. Yeah. This is also true for any kind of hit. Like if I'm hitting this, this side is going to move, like this side is going to move when I hit this side. That motion travels as a compression wave through the entire object. Travels as a compression wave through the entire object. It happens so quickly that it looks like the whole object moves at once, but in reality, it actually has a direction of travel. Yeah, there's some really great videos for that I'm going to show during the live class. I don't have time to show those videos here because we have a lot to get through. Yeah, now the other type of wave, remember I said there were 3 types, is surface waves. And surface waves have a little bit of both. So they have a little bit of transverse and a little bit of longitudinal. So here's the direction the wave is going. It's going that way. See it moving that way? And the particles here are moving in kind of like a figure 8. Not a figure 8, sorry. They're moving in a circle. So they're moving a little bit forward and back and a little bit up and down. And that creates a surface wave. It's got a bit of both. There are 2 types of surface waves. This one in particular is called a Rayleigh wave or a Rayleigh wave. Water waves are such an example. They move in circles. So the particles move in circles, but the wave moves in a line. The particles move in circles. So a lot of people say that water waves are transverse waves, but have you ever seen water do this? No, water does this. So water waves are surface waves, specifically Rayleigh waves. And this is why water waves break when they get near the shore. This circular motion of the water, when the bottom circular motion hits the shore underneath, they kind of stack up and then it falls over. That's why you get this circular motion to the wave, because the particles are already trying to move in a circle. So that's Rayleigh waves, essentially. Earthquakes can actually have all 3, so this is kind of an interesting description of all 3 waves. Earthquakes, when you shake the ground, think about like shaking, not that, but this, shaking this and hitting it, right? You're going to get a compression wave traveling straight down from where you hit, straight down through it. And you're going to get transverse waves going along here. You're going to start moving it side to side and up and down and stuff. And it's also going to have some twisty motion, right? A little bit of twisty motion and some jiggly motion and stuff. So you get all the different kinds of waves. The first wave, that compression wave, is the P wave, the primary wave. And it moves very, very quickly because it's solid particles of Earth trying to get away from solid particles of Earth. They're hitting into each other. Very, very fast wave. The secondary waves is the entire surface going side to side together. So together, side to side together. And it's the second in terms of speed. They're slower than the primary waves. They're a little bit more damaging because it's moving side to side instead of pushing right through. And then the surface waves, Love and Rayleigh waves, are that rolling motion, or you can have a twisting motion. So the particles are moving in a twist kind of direction. These cause the most damage because of that twist. You don't want to twist stuff like buildings and highways and bridges and stuff like that. Those are the ones that make the most earthquake damage. But they are the slowest, which is important because these move fast and have the least amount of damage. It can lead to early warning systems where the primary waves are detected, and then very quickly like a tweet is sent out, and people can actually go and seek shelter before these guys get there, just because these have gotten there first. It's really interesting to feel when you're actually in an earthquake. When I lived in Japan, there was one big earthquake, and I actually felt the difference between the primary waves and the secondary waves. The primary waves were like a truck going by outside, just like a basic rumbling. Then when the secondary waves hit, everything started moving side to side. It was really, really, really cool. All right, that's that. We're moving to the next section, which is other wave features. So I'm going to pause that there. Okay, and we're back. We're going to do other wave features. Keep in mind here, all three types of waves have an equilibrium, a period, an amplitude, and a wavelength. So if I jump back to the earthquake thing, right, the P wave, there's some kind of equilibrium, the amount of compression that the ground likes to have, and this is too compressed and this is too spread out. The S wave, there's a certain place where the ground would like to be, and this is too far left and this is too far right. Same with the Rayleigh wave, same with the Love wave. They have a period, so the time between two wave fronts. They have an amplitude, so how far away from equilibrium they are. And they have a wavelength, which is the distance between two wave fronts. So that's what we're looking at here on a transverse wave, but it exists on all kinds of waves. Sound waves have a wavelength. Sound waves have an amplitude as well. This is what we're looking at. The first one, easiest one, is probably amplitude. Amplitude is how far up and down it goes. Here's my wave structure thing. I'm going to move this back to the right, and I can change the amplitude. If I have a big amplitude, you see it's going up and down a lot. If I have a small amplitude, it's not going down a lot. Okay, I'm going to change the frequency here just so you guys can see a little bit better. Right, here's, and I'm going to put it in slow motion. Notice the wavelength, the distance, the size of the wave. I'm going to change the amplitude to really big. And you get the same distance between a wave. Here's one wavelength there. We have one, two, about 3 waves that fit in one. All right, if I pause there, 1, 2, 3 waves-ish that fit. If I bring down the amplitude to something very small, maybe not that small. So I'll go a bit faster here. All right, 1, 2, 3 waves fit. So it's the same wavelength, even though we've changed the amplitude. The amplitude does not affect how fast the wave travels in general. So that's the amplitude. More energy makes a bigger wave, but not a faster one, because you're moving further away, which means you get more returning force, but because you're moving further, that force has more distance to act over. And so it takes the same exact amount of time, whether you're far away or close, to get back to equilibrium. But it does lead to more energy in the wave. It's based on whatever we can observe about the wave. So for water waves and spring and earthquake and my balloon, right, the amplitude is how far away from equilibrium I can take it. How far away from equilibrium. So there's the amplitude. There's a little bit of amplitude. There's more amplitude. And you can see it's going to be louder there than it is there. For sound waves, it's a pressure difference, an air pressure difference between the normal air pressure and whatever the highest or lowest air pressure you get in that room is. The wavelength is literally the length. So here the wavelength is however many meters that's going to be. Right? Literally length, like in meters, always measured in meters. The wavelength is how long it is from a crest to a crest, or a trough to a trough, or maybe from some random place to some random place, as long as it's in the same place. That's the wavelength. Yeah, it's the length of the wave. It's measured in meters. The symbol is lambda, which is the Greek letter lambda. It's the Greek letter L. And you draw it like this. You know, do your best. It's kind of an interesting one to draw, but it is literally just the length of the wave. How far it is between a crest and a crest, or a trough and a trough. Next up, frequency and period, and please enjoy the absolutely horrible kangaroo gif here. I leave this here just because it's particularly awful. So I'm going to move my face out of the way just so you can see that even better. This bottom kangaroo? Nope. That's just not right? It leaves the waveform behind. And this top kangaroo is even worse. It also leaves the waveform behind. I don't know who made this gif, but it's awful, and I love it. Frequency and period are very related. Period is how long it takes for a wave to go by. and frequency is how many waves we have in 1 second. So here, when I have a frequency of 2 hertz, you'll see the wave going back and forth twice a second. A frequency of 1 hertz means once a second. So if we bring it down to here, 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, once a second. 2 hertz means twice a second, 2 times a second. 3 hertz, 3 times a second. 0.1 hertz means it'll take 10 seconds for us to see a wave go by. 10 seconds for a wave, because basically a tenth of a wave goes by in a second. But those 10 seconds, right, 10 seconds, I said there's 10 seconds for a wave to go by, that's the period. That is how long it takes for one wave. So this wave has a frequency of 0.1 hertz and a period of 10 seconds. This wave has a frequency of 0.5 hertz, so it'll take 2 seconds to make a wave. A frequency of 1 hertz, 1 wave per second, means that it also takes 1 second to make a wave. A frequency of 2 hertz, 2 waves per second, means that it takes half a second to make a wave. So frequency and period are intrinsically linked. Period, big T for time, is the time it takes for one cycle. Frequency is not cycles per second, it's measured in hertz, just dead white guy. It's 1 over seconds, or seconds to the negative 1, but a lot of people just use hertz. And it's a very useful idea. There's an easy conversion. The frequency is 1 over the period, and the period is 1 over the frequency. So they're just reciprocals of each other, if we use the math term for it. Next thing is, if you know how long a wave is, how many waves go by in a second, you know how fast it's going. Because you know how long it is, which is lambda, and you know how many lengths of the wave go by in 1 second. So you can get the speed. Right? So here, for example, you have the frequency. You'd have to figure out the wavelength, but you could know how fast it's going because you know that there's 2 every second. And so there's 2 of these, 2 waves go by a certain point, like where my mouse is, every second. And if you know how long one wave is, you just multiply how long one wave is by 2. You know how many meters of wave went by in a second. That's called the universal wave equation. Speed of a wave is the frequency times the wavelength. It's very important to note that that says nothing about the amplitude, right? The amplitude has no bearing on this stuff, on this wavelength. So V equals F lambda. You can also get V as lambda over period. That's another option for that. So those are other wave features in the universal wave equation. We're going to do some practice problems. So I'm going to pause while I change this. Okay, we're back off pause, and we're going to try some different practice problems. We're actually going to start with number 2 here, because it's easier to start with number 2. So tuning fork's tines vibrate 250 times in 2 seconds. We want to find the frequency of the vibration and the period of the vibration. So we'll start with the frequency. Frequency means how frequent, how many times in 1 second. It's 250 times in 2 seconds. So we go like this. It's number of cycles per number of time, right? Number of cycles over time, which is 250 cycles, which is how many times the tuning fork vibrates in 2.0 seconds, which is obviously 125 hertz. Remember, cycles per second, that's hertz. But with significant digits, we have to round that because we only have 2 significant digits on either one of these numbers, and it's exactly 5, so we want to go to the make it even policy, so 120 hertz. Frequency is cycles per time, cycles per second. Now the period is asking us how much time for 1 cycle. How much time for one cycle? Well, we know we have 2.0 seconds. And in those 2.0 seconds, we have 250 cycles. So to get the time for one cycle, you just take 2 divide by 250, and you just need to grab a calculator and do that. So 2 divided by 250, 0.08008, and then we need a number here, or a unit, and cycles is just a count. There's no unit there. It's just a count of how many cycles there are, so it's just seconds. 0.008 seconds. But significant digits, we had 2 significant digits here, so we have to throw in another 0 to show that we have 2 significant digits there, and those are the answers there and there. Okay. So there's our first practice problem done. I'm going to actually change the color here so that it doesn't look so confusing. This one's red. This one will be blue. Okay, now we're going to convert the following frequencies into periods. So 340 hertz is a frequency. It's how many cycles? 340 cycles per second. Which means that one cycle will be done in 1/340th of a second, if you're getting 340 of them in 1 second. So here we can go, period is 1 over frequency. Right? And that is, I'm going to shrink that. There we go. Period is 1 over frequency. Period here is 1 divided by 340 hertz, which is a very small number, whatever that very small number is. So 1 divided by 340. Let's grab the calculator, which I put over here. 1 divided by 340. 0.00294 seconds, because hertz is actually 1 over seconds. It's seconds to the -1. So 1 over seconds to the -1, you get that much time for one cycle, except there's only 2 significant digits, so it's actually 0.0029 seconds. So that's that one. We'll make it purple or something. Yeah, purple sounds good. Let's try another one. 20 cycles per second. Cycles per second is exactly the same thing as saying hertz, so we get exactly the same setup. Exactly the same setup, except instead of 340, we have 20. 20 hertz, and 1 over 20 is 0.05 seconds. And we only have 1 significant digit, so we only leave 1 significant digit. This one, 0.033 seconds to the -1. Oh no, it's less than 1. Well, it's the same thing, right? Period is 1 over frequency. It's 1 over 0.33 hertz, still in hertz. And so that's going to give us something like 3. So 1 divided by 0.33, 3.03 seconds. But we've only got 2 significant digits, 3. So we want this to 2 significant digits, it's 3.0 seconds. And that's how you convert them. Now the last one here is talking about finding a speed. The next one here is talking about finding a speed. Speed of the sound wave. The wavelength is 35 centimeters. So lambda is 35 centimeters. 35 centimeters. I'm going to actually pause and find a lambda symbol for us. So I found a lambda symbol. Lambda is 35 centimeters. And the frequency is 1,000 hertz. So frequency is 1,000 waves per second. 1,000 waves per second. So 1,000 waves per second go by. 1,000 waves go by every second. Each one of those 1,000 waves has a wavelength of 35 centimeters, which I might as well just turn into meters because we're going to be needing that. So 0.35 meters. And the frequency is 1,000 waves per second. So 1,000 of them go by every second. Each one wave is 0.35 meters, which leads directly to our equation. V is F times lambda, which is frequency, 1,000 hertz, times 0.35 meters. Remember that a hertz is a 1 over second, right? Hertz is 1 over seconds, 1 over seconds. So it's going to come out to meters a second, which means that it's 350 meters per second. But we only have one significant digit here, so make it even. It's actually 400 meters per second because of significant digits. I'm going to stick the little tilde in there. There we go. And then this one here, I'm going to push this over to the other side here. 1/4 of a wavelength is 0.85 meters long, and the frequency of the wave is 125 hertz. So let's find the actual wavelength. Well, if 1/4 of a wave is 0.85 meters, the full wave is going to be 4 times 0.85 meters, which is whatever 4 times 0.85 is. 3.4 meters. Right, 3.4 meters. The frequency is 125 hertz. So the period is 1 over the frequency, 1 divided by frequency, which is 1 divided by 125 hertz, which is, we actually did this earlier here. We did it back here, because it was 125 hertz, so it's actually 0.008 seconds, 0.8 seconds, 0.008 seconds. I'll change some colors here real quick. Red, blue. Now the velocity of the wave, we have the expression is v equals f lambda. V equals f lambda. So which one are we taking here? What are we taking from our question? Well, lambda is the length of one entire wave, right? It's not the 0.85, it's the full wave, 3.4 meters. And the frequency, which I guess we should put first, right? Frequency is first. Which of these is it? It's 125 hertz. We're not using 0.008, we're using the frequency, 125 hertz. Hertz. And that gives us whatever the wave speed is. So 125 times 3.4, 425 meters per second. And then we have to do our significant digits. We only have 2 significant digits here. 2 significant digits. So this needs to be 2 significant digits. Make it even, 420 meters per second. And that's how you do that. So I'm going to turn that purple. And that's some wave practice problems. We're done with some of our wave practice problems. Next up, we're talking about interference, wave superposition. I'm gonna talk about this in Monday's class, so I'm just gonna stop it here. But the important piece here is because it's energy, it'll move right through itself. So notice these ripples that I'm making on this ripple tank, which of course I'm gonna have a link to down here. They just move right through each other. And I can go to a 3D view and you'll see them moving right through each other. They just move straight through each other. They don't even see each other being there. But if I let them interact, and I'm going to let them actually interact here, and go to the 3D view. One thing to notice is that right where the energy is stacked up, remember that the energy is related to the displacement. We've got one displacement coming one way, one displacement coming the other way. Both displacements end up stacking up on each other. So that's what interference is going to be about. That's what this part's going to be about. But that's for Monday. We're going to leave it here with basic wave problems. And yeah, we're going to do some practice problems in class. Thanks for listening, and I'll see you there. I'll see you on online lessons.